continue. There we go. We're now recording. Good. And radial basis functions. Before we get to the actual radial basis functions, and again, the book does a good job of describing where these come from. I want to talk about sort of basis functions in general and where this comes from, because this mathematics, I think, will be generally helpful. Most of you are familiar with the concept of a vector space, although you may or may not have called it that. Vector spaces are, as you can imagine, spaces of vectors. But in the most abstract sense, what they have that makes them a vector space is they have they have these two things. There's a norm. Let me get this going here. There's a norm, and there's an inner product. And so, just like other spaces and the concept of topological spaces or basic mathematical spaces, sets, rings, groups, things like that, these spaces have a structure. You'll notice that there's nothing about this structure that says you have to use a vector specifically, although vector spaces, vectors, there's groups of a finite number of real numbers organized as a vector are of course the most common vector space that we deal with. But it's important to realize that you could have the elements within this vector space. We tend to think of them as looking like a finite element vector here, but there's no reason why it couldn't be an infinite vector, why these things couldn't be infinite. And also have norms and inner products. Of course, once you're dealing with infinite, you have to worry about whether the norms and the inner products converge, because these are now convergent sequence. These are now sequences of things or series, right, where you're adding large numbers of things, and so they have to have finite values. But there's a norm and an inner product, and the norm and the inner product are related by this. They must be related by this, such that the inner product is the square root of the norm. Excuse me, this should have been x with itself. I apologize. So what it should be is, you can think of it, x squared is equal to the inner product of x with itself. And that inner product is written in matrix in standard vector notation, might be x transpose x when x's are vectors. But remember that x's are not always vectors, and this concept of x transpose x as a way of writing it may sometimes even apply to things that are infinite vectors, but well defined, right? And because you can imagine that's just the sum of xi squared, where I equals 1, possibly up to infinity or up to n or up to something else, right? So it's a well-defined concept. Now, vector spaces are a little bit more have a lot of complexity to them. The norms themselves have some significant complexity. These things these must satisfy the triangle inequality, which is basically that the norm of x plus y has to be strictly, well, less than or equal to the norm of x plus the norm of y. Right? So, excuse me, only if I write this properly, less than or equal to the norm of x plus the norm of y, right? So those are basic requirements on norms, and some of you have seen those things. A Banach space is smaller than a vector space in the sense that it just has a norm but may not have an inner product. Okay. And you can imagine that's just a group of things where you can determine what their size is. The size follows a triangle inequality, but we don't have any simple ways of taking products between them. There's a lot of requirements on what you need to do to be an inner product. These things have to be linear in each of their elements, and there's things there. And I'm not going to go into all of the formality of that, but just to give you the basic definitions of these things. The thing that we're going to be talking about mostly are the class of Hilbert spaces. And Hilbert spaces are basically, for the most part, behave exactly like vector spaces. The only difference is that these x's aren't really, they may be vectors, but as I was saying before, technically they can be absolutely anything. And usually when people are talking about Hilbert spaces, these x's are actually functions. And the reason that's important is because where x here may look like a collection of real numbers, in this case, in a function space, it could be there's x could look like some function of t, right? It could just be a collection of different functions, and something else might be g of t and h of t. You could have, so it's just a collection of functions, but you can imagine that you can define inner products on functions, and you could have norms of functions. And the tricky thing here, of course, is that functions are very big things. There's a lot of them. and they themselves have complicated properties. And so now you really have to worry a lot about whether these inner products and norms converge, right? These are now operations on functions, and lots of things go wrong when there's operations on functions. So the way to think about it is a Hilbert space is like a vector space for functions. Hilbert spaces themselves can be finite dimensional. And finite dimensional, we'll talk a little bit about what we mean by the dimension of a function space, but they can be finite or infinite dimensional. But one way to think about it is an infinite dimensional Hilbert space behaves sort of like a very delicate vector space. That there are lots of ways in which things cannot be Hilbert spaces. They may not converge. Limits may not exist in the way that you think. So you have to be a little bit careful about that. And lots of things that you'd think would behave like norms are not in fact norms. So for instance, we talked last time about the idea of the L1, L2, and L infinity norms. And if you want to remember what those look like, the L2 norm is the common one, looks like the sum of f squared x dx. The L1 norm looks like the sum of the absolute value of f of x dx, and the L infinity norm looks like the maximum value over whatever your range is of f of x, right? Usually the absolute value. So those are ways in which you could measure the size of a function, but only the L2 norm allows you to create a vector space, because the other norms, the L1 and the L infinity norm, cannot be written as in the L2 norm has the property that the norm squared of x can be written as an inner product of f with itself. Excuse me. Get this. It's as an inner product of f with itself, but the L1 and L infinity norms cannot be written that way, so that they do not satisfy the requirements for norms that are part of vector spaces. Although they are valid norms, right? So you can create a Banach space out of those. You just cannot create a Hilbert space out of those. Okay. So for almost any time you're talking about Hilbert spaces, anytime you're talking about sort of functional groups of functions or spaces of functions, you're almost always using the L2 norm, and that's the importance of that. There are other ways to make spaces. There are other ways to do things that get very tricky. There's this shows up a lot in control theory. For those of you familiar with H infinity control theory, there are ways in which you can extend the L1 and L infinity norms and use those as part of spaces. But a typical space that we're dealing with is the Hilbert space of square integrable functions. So you imagine one of the things that you generally want for these spaces is you want the norm to be finite for anything in that space, any function in that space. And that basically translates into the idea that over the range of this space, which might or might not be negative infinity to infinity, right? You can have the space of functions over 0 to 1. You could have the space, these are all, you're just defining what are the elements of that space. So the elements of this particular space I'm talking about here are the space of functions where when you integrate them from negative infinity to infinity, the integral of their square has a finite value. Right? And those are the space of square integrable functions, and that's important because that allows your norms to be meaningful. And it also means that your inner products will be meaningful. What we refer to as the space of L2 functions is again the ones that we use the L2 norm. So this, which is the L2 norm of f, sometimes people will put a little 2 there to make clear it's the L2 norm. The L2 norm of f, and this is actually the square of the L2 norm, is equal to that. That is this here. That becomes your norm, and then you have this inner product. And we often call this the induced norm because it's created from the inner product. We just define the norm to be the square of the norm to be the inner product of f with itself. So given an inner product, you can always create a vector space or an inner product on, given an inner product on functions, you can create a Hilbert space by using the induced norm as the norm of that space, right? So these spaces are a collection of a set of functions that you define, plus a norm on those, plus an inner product on those functions, plus the induced norm. Now, these are infinite dimensional spaces and usually uncountably infinite. And again, I don't want to go into all the details of this, but just to remember what definitions of things, the terms that you're going to hear, like countable and uncountable. There's infinity, and then there's bigger forms of infinity, right? So how many integers are there? There's an infinite number of integers, right? How many rational numbers are there? Well, there's an infinite number of rational numbers, but you can make a one-to-one relationship between the rational numbers and the integers. That's so you know, a rational number is the ratio of any two integers. And so the set of that because is exactly the same size as the integers, and there's a fairly standard proof of that I'm not going to do. But the real numbers do not have a one-to-one relationship with the integers. For any two real numbers, I can find an infinite number of things between them, no matter how close they are to each other, right? So that while, and again, this is true for rational numbers as well, but the point is there's no way that you can make a one-to-one relationship between the integers and the real numbers. And that's what we mean by uncountable. I can count integers, 1, 2, 3, 4, 5. You know, I can count, in theory, if you handed me a number of primes, I can count the prime integers, even if I can't identify all the primes. I can count rational numbers, but I cannot count I cannot count real numbers. So and this is important because when you think about functions, how many functions f of x are there? Well, if x is real, and that's usually what we mean, if x itself is real, the set of functions over the real numbers can take different values for every single value of x. So x is real, so there's an uncountable number of x's. That means that f of x has an uncountable number, and the number of possible functions is sort of the you know, that to the nth power. So even if f itself is binary, right? You give a binary function on the real numbers, there's still an uncountable number, right? Because that means that's 2 to the infinity, but 2 to the uncountable infinity, right? Of those. 2 to the countable infinity is countable, but 2 to the uncountable infinity is not countable. So these are very, very big spaces in terms of the size, the number of things that is within them. Okay. But that doesn't mean that they have to be that big. So if I restrict this space in some way, so I say I'm going to restrict this space to the set of functions that have continuous derivatives. Okay, and note that there's nothing about this definition here that says that those things have to have continuous derivatives or even have derivatives at all. But if I restrict it to the set of functions with continuous derivatives, that's a much smaller space. And I could restrict it to the set of functions with continuous derivatives that are band limited, right? That when I do the Fourier transform, there's a maximum frequency. And that becomes a much smaller space. So there are ways in which we can talk about spaces, which are still completely valid Hilbert spaces, that are that are much smaller, that may have countable dimensions. And I'll talk about, and that's what I'm about to talk about next. So there was one question: does Hilbert space, does X have to be a function to be a Hilbert space? No, it does not. The elements of Hilbert spaces can be anything, but usually this is the context in which they're used, and this is the context that we're going to use it. So suppose now that within this Hilbert space we have a representation of functions. So just like if I had a vector space, I might have different dimensions, right? I could represent any number in a vector space. So you have a two-dimensional vector space, by any point in my two-dimensional vector space by its coordinates along two different dimensions. That's a fine way to represent things. So I could do the same thing to functions. So suppose that I now have a function space, and what I want to do is I want to say, okay, let's suppose that I have a function phi1 of x here and a function phi2 of x there. Any point here, which could be some function f, might be a sum of a times phi1 of x plus b times phi2 of x, right? So this is still a two-dimensional space, right? I only have two dimensions, but every element in that two-dimensional space is a function, right? It's the space of all functions that can be written as a linear combination of these two functions, right? So that's a two-dimensional Hilbert space of functions. So although Hilbert spaces have the ability to be very big and they have the ability to have uncountable dimensions, they really don't have to be that big. So I could look at the space of functions here, this space of functions, where, for instance, I pick the set of functions phi, and maybe there's only n of them, and that we will call an n-dimensional Hilbert space. right? It still has, I still have inner products, I still have norms. There's just not as many functions in it, right? Because they're constrained based on this finite set of basis functions. Now, I could have picked an infinite set of basis functions too. For instance, suppose that phis are phi sub I is x to the ith power, right? That gives me a Taylor series expansion. Now I have the full set of analytic functions, right? These things are all continuously differentiable. They have infinite continuous derivatives. And I could have the set of nth order polynomials if it's only up to n, or I could put infinite here and I have the full set of analytic functions, right? So those phis can be anything you want them to be, but we can represent sets of functions like that. It could be xi. It could also be phi sub I. Could be something like the sine of some frequency. Let's call it omega I x plus some phase sub I. That could be a set of functions there. And now I have the Fourier basis, right? Again, if it's infinite, I can represent all continuously differentiable functions. If it's finite, then I get a finite dimensional Hilbert space, which is the set of band limited functions, which depend on, and those things will have finite, just certain frequencies that we allow them to have, right? And the phase, the way you do that is you actually have a set of basis functions that are the sine of omega I x. You also have pairs cos of omega I x, and then of course by combinations of ai, bi, by combinations of those things, linear combinations, you can generate arbitrary phases of all the components. So you can represent functions over these spaces, and depending on how you do that, you're going to get different behavior or different sets of functions within these spaces. But all of them still have a perfectly good inner product. So here's the inner product. Right. So what does the inner product look like? Well, again, look back up. We start up here from this inner product, and this inner product here tells you that's the general inner product that induces the L2 norm. And again, we tend to use the L2 norms for this. So here we have that inner product. And when I take the inner product of two functions that are written, both of them written as this sum of what we're going to call basis functions, what you'll see is that you end up, exchanging, when you exchange the sums and the integrals and all that, you get the integral of the sum of this sum here, right? And and again, we can do, if you think of these as g, fi and gi, these are countable. Well, in this representation, you notice that the coefficient and the basis functions are countable. It's possible to create Hilbert spaces over uncountable basis functions, but that's not a good idea. And I'll give us an example of that in a second. But in this case, note that I have a countable set of basis functions, even if it's infinite. That means that the coefficients can behave exactly like an infinite vector, right? Because they're just a series of real numbers that come in some order. So I can then write this thing here as sort of this sum over ij of fi gj times the integral of phi I phi j dx, right? And if you look at what this is, this integral thing here, let's call that integral. We're going to call these the elements qij, right? We'll just call each of those qij, right? And if we call each of those qij, then this thing becomes, we can write this as a matrix Q. And if we call all the fi's with an abusive notation, this is no longer the function. I should give it some other name, maybe f bar or g bar. These are the vectors of those coefficients, which may be infinite vectors. Then I can write like this. Actually, technically, there's no x there. So this could be written as f transpose q times g, right? Where I should put the little bars over these because I want to distinguish. In this case, I mean f, not the function f. I mean the vector of coefficients of fi, right? Which is this thing, the vector of those coefficients. And so I can write this operation, the inner product, looking like this this particular vector operation, right? The vector operation on the coefficients. And the reason I can do that is because the set of functions within this Hilbert space is all of the ones, and I've chosen this as a decision I've made. All of those functions can be written as a countable mixture of basis functions. So that means that this is now my inner product, and that means that induces this norm, F transpose QF. So I now have an inner product and a norm, which looks surprisingly like vector operations, right? I mean, if Q is the identity, then these are your standard vector operations. It's just they're performed with the little bars there. They're performed on the coefficient vectors, not on the original functions, right? So if these the basis functions are orthogonal, by which I mean that the integral of phi I of x, phi j of x dx equals 1 if I equals j and 0 if I does not equal j, right? In other words, these functions don't, it's the same concept as orthogonal vectors, right? Y transpose x equals 0. If y does not, it says that they're pointing in different directions. So if I choose a set of basis functions that have this particular orthogonality property, then Q is the identity, right? That's just what it means. This, would be this integral here is that integral there. So Qij is equal to 1 only if it's the same basis function, and if it's different, then they're not. Then I will actually recover things that look exactly like the vector norm. But if these are not orthogonal, then you will have this Q term in the middle there. Does this make sense so far to people? Let me know if this is getting confusing. We're moving very fast, but I'm trying to make the link back to vector spaces.
I actually had a very different question, just about the order for the lectures that we're having. Because today we had the pre-homework was still on the backprop multilayer perceptron. Not on radial basis functions. So I thought we were going to continue the backprop lecture that we started last week, or did we finish that already?
Basically finished it, so I moved on to the next one, which makes me realize that we may be one lecture ahead of where we need to be. I'll double check it on the schedule.
Okay.
But that's fine. I'll take a look and I'll correct that if I got that wrong. Because we made it through most of backprop last week, even an extremely long chapter.
Yeah. All right, just checking. Thanks.
Yeah. We're going to come back to backprop a little bit later in this lecture, so there's aspects there that will be relevant as well. Also, the stuff I'm talking about now is not in the book, so that's we can go. This is so. Anyway, but I just want to make sure. I mean, some of you have probably seen this stuff before. I suspect most of you have not taken functional analysis courses, but I want you to think about this, because this is the realm that we're about to get into. And the point I'm trying to make is that these Hilbert spaces seem like very complicated things, but in the end, they behave exactly like vector spaces. And in fact, there's this analogy. What this allows you to do is you're going back and forth between coefficients. This has become such a mess. I'm going to get rid of some of my things around there. What this thing allows you to do, circle it in red for fun, is it says that there's a direct correspondence between these vectors and functions. And where we're going to go with this is that operations on functions can be done as operations on vectors. So I've already shown that the two most basic operations on functions, inner products and norms, have vector equivalents and that look exactly like the thing in the vector space. Let's see, I'm just gonna, there's some background noise that I'm gonna take care of. Good. So that's what I'm pointing out here. There's a one-to-one match between the infinite dimensional vector space of coefficients and the infinite dimensional Hilbert space, and note that the vector space of coefficients is countable is countable infinite, but the Hilbert space of functions may be uncountable infinite. Right, so that's a very important thing. Now, it's not, of course, you've only got one space. It's either countable or it's not countable. But if you just start out with a space of all possible functions, that's uncountable. I'm restricting it to have a countable dimension, right? And it's still infinite dimension, but countable dimension. So this space of functions here, circled in red, has a countable dimension. This is smaller than the set of all possible Hilbert spaces. Yeah. All right, so now let's get back to function approximation, which is where we're going to go with our radial basis functions. But let me come back. Again, I haven't talked about radial basis functions yet. Suppose we have a desired function f star of x, which is already within the Hilbert space, right? So that means that I can write f star of x as a combination of the basis functions phi. And now suppose I want to approximate it using something else here, right? Using a function within the Hilbert space. Well, there's an exact solution, right? Obviously, if I can find bi equals ai, then f hat will in fact equal f star, right? So this has an exact solution, and you can solve it using any one of your standard linear methods, right? This is, and in this case, I'm writing this as r phi phi, where phi might be the vector. I'm defining phi to be this vector of phi1 of x up to phi n of x, even if n is infinite, right? But I'm just defining this to be sort of the output of my functions here. And for all practical purpose, we're always going to be dealing with finite dimensional vector spaces, just because that's all we got. So that's all we can compute. So you're going to have a finite. So phi is this vector of the outputs, and it's a function of x. And so I can calculate for that function of x. I can take phi of x times phi of x transpose up there. I can look at the expected value of that over x, and I'm going to call that thing r phi phi, right? Just like you would for anything else. And the image that you want to have is the image that of these radial basis functions. So this thing here is phi1 of x down to phi n, let me write this, sorry, I messed up, to phi sub n of x. So and I can look at these outputs, and that's just a big vector. And then I'm going to have some weights going here. And so the output here is the sum of wi phi I of x, right? So that's how the basis functions get generated. And you'll notice that the inputs to these basis functions, which could from x, if x is multivariate, right? Phi1 of x, this could be x1, x2, x3. Phi1 of x might take components from all of these. All three of these might somehow feed into phi1 of x. This is a scalar. Right, so that you have a vector input can go to a scalar like that, but doesn't even have to be that way. You could also have, it's perfectly valid to have a network where x is just a single number, and then you've got a bunch of phi sub i's here, and you could just have that single scalar. Phi sub I of x is a scalar, and then you combine those with a bunch of weights here, right? So that's all. These are all valid forms of basis function networks. I call them radial. I haven't said anything about radial yet. So this could be a scalar. This could be a vector. It doesn't matter what x is. Right? These could be images, they could be anything. But the point is that these functions have scalar outputs, and then they're recombined. In fact, they don't even have to have scalar outputs, but you don't gain anything by making it not scalar outputs. Okay. So function approximation within the Hilbert space, this is like saying, suppose that I have my desired function is a neural network. Suppose it actually is a built from a connectionist network, and I'm just trying to find out the weights in this network. You handed me a network with weights in it that I don't know, and my goal is to find those weights. So I know that I can exactly match that network. It may not be unique. There could be a different set of weights that solves the same problem. So I might not get the same weights you do, but I will always get zero error, assuming my learning algorithms work. Okay. But Of course, in reality, it's not like that, right? The reality is we're dealing with something in the real world and we're trying to approximate that. So now f star of x does not live within the same Hilbert space. But the way we tend to analyze this, and here's where the power of Hilbert spaces becomes very, very helpful. We can say f star of x lives within some other Hilbert space that we may not really have access to. And what it really is f star of x it lives a little bit within our Hilbert space, which is this part. But then there's a whole bunch of other basis functions that we just don't know about. These are all the things that we don't understand, that we can't measure. It could be the noise components. It could be all sorts of things that we just don't have access to. And our goal, again, is to approximate it within our Hilbert space of functions, right? So for instance, this might be finite number of those, but there could be an infinite number of these things. So a typical example might be approximate some signal that's coming in using a band limited signal, right? What's a low pass filter? A low pass filter finds the best approximation within the set of band limited functions to the non-band limited signal that's coming in. That's what a filter does, right? It says I've got a function, comes in some radio signal that has frequencies that for the most part go up to infinite. I mean, they may be very small, but you can imagine, some radio signal coming in with visible light and gamma frequencies and all of that. And I want to filter that into the AM radio band. And so what I'm going to do is I'm basically finding my best approximation to that within the AM band. Or I could have a measurement of temperatures over time. I want to know how does temperature fluctuate on a year-to-year basis. So I'm going to low pass filter that, and I'm going to find the best year-to-year approximation of the temperature fluctuations, which may be changing a little bit every single day. So that's what's going on here in the world of Hilbert spaces. And so what I'm doing is I'm finding the approximation within my finite dimensional Hilbert space to the infinite solution. And we know what those answers look like, right? It's all usually based, the one way to think about this is based on the triangle inequality. The best approximation is formed, so when you've probably done this within your vector courses, just vector algebra courses, standard linear algebra. If I have a two-dimensional space, x1 and x2, and I want to find the best approximation within the one-dimensional x1 space to a point in the two-dimensional space, the answer is always to project down with a right angle there, right? The shortest distance, anything else, will be a longer distance. So the shortest distance from the true answer to my best approximation always forms a right angle here, right? That's true in linear vector spaces, and it's true in Hilbert spaces. And so because it's basically exactly the same mathematics. So the shortest distance, and remember our distance metric here is measured in terms of my, things like the L2 norm, right? So the shortest L2 norm, which turns out to be the mean squared error, right? Remember, because the L2 norm of a function, even an error function, which I'm going to write as tilde like that, looks like this thing squared dx, right? So that's the L2 norm. That's the sum of the squares of the errors. This thing has to be squared. So that distance, the sum squared errors, is minimized when we project. We do the orthogonal projection of the thing we want, gets projected orthogonally onto the space that we're trying to approximate. Does everyone get that? Have you seen this before? Has anybody not seen that? Should I show it in more detail? Again, that's standard linear algebra. You probably haven't seen it in the functional domain. But please stop me, because there's good insight into all of this, but I don't need to rehash this if you've already seen it in linear algebra courses. When you do that projection, the linear approximation we talked about before this doesn't change. It's the same thing. That's what this does. This is the answer to that question. And here you notice that these phis are the low dimension. It's the stuff we have access to. So this is very nice, right? That this basically says all you need are the outputs from the basis functions, this thing here. All you need is the outputs of the basis functions and the correct value of f star, and then you can use any algorithm to find the weights. You don't need to know this. You don't even need a model of that, right? Because this will always find you the orthogonal approximation. It's going to find you the minimum error approximation. And it's always going to get you that right answer. And so the point is, everything we learned before, how do you train the weights at this level? How do you train these weights? You can just use any algorithm you want. You can use LMS. The book suggests an algorithm called recursive least squares. There are you could just find it. You can just directly invert the matrices or find the pseudo inverse of the matrix. There's lots of ways in which you can find that. You can do it by batch. You can do it iteratively. There's lots of ways to find out. So the idea here is just like before. What we were doing is we were starting with a set of values x. Maybe this is x1 to xn in LMS, and we're using, and these are the weights, and we used LMS to train the weights. Delta W looks like gamma of y minus y hat times x, right? That's the standard LMS algorithm. These, instead of being x's, could be phi1 of x to phi n of x. X is here, goes out like that. And now we just do the same thing, except instead of this thing being x, this thing becomes phi of x. So no subscript on it, sorry. This thing becomes phi of x. Same algorithm. So in the end, after all of this math, you get back to what you knew anyway. But the point is that it's now a lot more powerful, because what you've done is now you have nonlinear functions. So now the output of this thing here, that's y, that function y is equal to the sum of wi phi I of x, or we can write that as w transpose phi of x. Right? Instead of just being w transpose x, which is what it was before. So w transpose x, this thing can only do linear functions. This thing can do nonlinear functions. And in fact, what I'm trying to point out here is that these phis can spread out x. You could take a one-dimensional x and have a 100-dimensional hidden layer. You don't get anything in the linear case. You don't get anything by doing that, right? If I were to do this in the linear case and take a one-dimensional x, suppose phi I of x was just equal to, some number, maybe I times x. Right, so I do the 1x, 2x, 3x, 4x, right? I don't gain anything by doing that, because these weights could have done, they already have that power in them. So I gain nothing by if phis are linear. But when phis are nonlinear, I can gain a lot, because now I can move into these Hilbert spaces. They're finite dimensional Hilbert spaces, but they still have a lot of functions to them. Functions in there. And in fact, these hidden layers, you could have 1,000 units in there, millions of units in there if you want. And that gives you the ability to approximate much larger classes of functions, nonlinear functions. So far we've been talking about basis functions in general, basis function spaces. Nobody calls them that. We can call them function spaces or Hilbert spaces, but sometimes in the network world, people refer to these as basis function methods. So radial basis, why radial? What do you get for being a radial basis function as opposed to a non-radial basis function? Well, first of all, what is a radial basis function? Radial basis functions are functions that, let's see, I don't think I didn't talk about exactly what they are. Radial basis functions are, as you'd imagine, radial, which means that they have the form phi sub I of x is equal to some nonlinearity times x minus usually some kind of center. So what does that look like? Suppose that H is sort of a Gaussian. So we'll make that H of whatever its argument is. Looks like some sort of a Gaussian. And if we're in one dimension, if this is xi, then this H of x minus xi gives you a little basis function that looks like that. If I had a different, so this might be x1, let's put x2 over here. I'm going to get a function like that. Let's put x3 over here. I'm going to get a function like that, right? Now, if I take these functions and I multiply them by some kind of a coefficient, let me make a little bit more space. So now let me take those functions and I'm going to multiply the first one by something low and the second one by something big and the third one by something low. And if I add them all together, I'm going to get a function that looks a little bit like that. right? So that's going to be my my sum function is going to look like this. And so this is now the, that's the function that might be, 2 times phi1 of x plus, plus maybe 5 times phi2 of x plus 1 times phi3 of x, right? And the only thing that makes one function different from the other is where I put the centers, right? So I'm just moving these centers, but these are now x1, x2, x3 these are just parameters at this case, right? Maybe I shouldn't use the same, again, the notation I'm using for multiple different things, but recognize that what I'm meaning here. So you have these little center points. And so this is basis functions over, I can put together, I can create functions out of this. And you can imagine that if I put these things close enough to each other, if I had lots of little spikes that were close enough to each other like this, I could approximate very smooth functions, large numbers of smooth functions. And if I had a lot of these things, I could approximate things that are not so smooth, right? So this might be something like that. You can imagine approximating fairly complex functions out of these. In the limit, as these radial basis functions become very, very narrow, they could become delta functions, right? So these could be things that actually are spikes. The problem with the delta functions is now how many of them are there, right? Well, you can put a delta function at every value of x. There's an uncountable number of those. But remember, I said these basis functions have to be countable. So you can't quite do it at delta functions because there will always be gaps between them, and those gaps will include an infinite number of real numbers between an uncountable number of real numbers between every gap. So it doesn't work if you go all the way to delta functions. There always has to be a little bit of smoothness to this, and that's but they can still be quite narrow if you want functions that move very, very rapidly from one to another. In higher dimensions, in a 2-dimension, radial basis functions look like you might have little centers at a bunch of different spots. And they're sort of radial from that, right? They look like little mountain peaks. Every single one of these things is sort of like a mountain peak. And I'm taking those mountain peaks and I'm adding those together, and I can now make a, if I could draw this in 3 dimensions, I can make, by putting all these mountains together, I can make some kind of a surface out of this, right? So I can make a surface out of that, and you could do this and so on into higher dimensions. What do radial basis functions get you? Like, why radial as opposed to something else, right? Because I could, of course, have done the same thing with sines and cosines. I could have done this with polynomials. There's lots of different bases that could have been used for this. The reason this is helpful is because these radial basis functions aren't that close to each other. So if you look at this basis function here and that basis function there, they don't have a whole lot of overlap. There might be a little bit of overlap here, but not very much overlap. So if I were to take all these basis functions and I construct that matrix Q I had at the beginning, right? Remember, Q ij is equal to the integral of phi I of x, phi j of x dx. If I were to create that matrix, then it turns out that most of these elements most of them are going to be 0, right? This phi I multiplied by that phi j is going to be 0. So this Qij matrix is going to have some values along the diagonal and pretty much be 0 off the diagonal. In the extreme, there'd be no overlap between these. But for radial basis functions, there's always a little bit of overlap. Again, if it came down to 0 overlap, you'd have zeros in your function approximations. You don't want that. So there'll be some overlap there. But the point is there's not much overlap. And that can be helpful when you're training things. So if there were no overlap, then the output of each basis function is independent of the others, right? It's or uncorrelated with the others. So that in that case, you would have this case, right? You have this uncorrelated outputs. If you have uncorrelated outputs, then learning under LMS becomes very easy, because if you do, again, if you look at these kind of things or the LMS rule, suddenly the outputs, if these things are uncorrelated, this term disappears. Learning now is completely local. Each weight depends only on the input and output from that weight. That makes things go really quickly, right? You can train one weight, and then if you train something else, it doesn't mess it up, right? If I have 2 weights coming in here and they're being summed, if I make a change to weight 1, Sometimes now a next value of x comes in. Sometimes, or if that causes a change to weight 2, that might require a change to weight 1 for other values, right? Every time I change one weight, I might have to change all the others, unless these are uncorrelated. If these things are uncorrelated, then I can learn each weight independently over the set. I could do batch learning for weight 1, I could do batch learning for weight 2, and the rate of convergence becomes much, much faster. So one of the things that radial basis functions do is, by making these matrices almost diagonal, they speed up the rate of learning. If I learn on one basis function, it doesn't have much of an effect on the other. And think of this so in the Fourier series, it turns out that different frequencies are orthogonal to each other, right? If I take the integral from negative to infinity of sine x and sine 2x, right? You know that thing is equal to 0, right? At different frequencies are always orthogonal to each other. So that's a basis set where you can calculate individual coefficients just knowing just off one basis function at a time. And we know this is the basis of the inverse Fourier transform, or the Fourier transform itself, right? So if I'm going to represent f in a Fourier transform as the sum of omega I, let's assume it's an odd function, so I'm just going to use sine wi sine of some, and you said something for frequencies. Well, I'll try and make omegas and w's different. That's going to be too much of a mess. I'll call that ai sine wix. Suppose that f is the sine of those things. Right? How can I find these ai? I just take that f of x sine omega ix dx, right? And you notice that I could find this value only by looking at the sine component of this thing, right? So the point is, I didn't need to know the other coefficients to find this coefficient. It doesn't matter, right? I can find the value at any one frequency without knowing the values at the other frequencies. And that's important over that basis set, because it's an orthogonal basis set. The radial basis functions are not an orthogonal basis set. They do have cross correlation, but only nearby. So this means learning is essentially local. It's not completely local, but it's local. If I make a change in the weight at one point, it will affect the weights around me, but just the ones around me. It won't affect very distant weights, and that also speeds up learning tremendously. So that's the idea behind having local basis functions. Again, this is radial in the sense that the value of the output depends just on the distance to these centers. It doesn't depend on which way you get to that center. But there's lots of other ways in which you can do this. For instance, you might decide that you would like your radial basis functions to be more elongated in one direction than another. And you can certainly do that rather than using this norm, because remember, you get to choose this norm, right? So it's just some function h applied to the norm. Now that norm doesn't have to be x transpose x. That norm could be x transpose qx, right? So you could anything that's a valid distance metric. And in this case, you could even use the L1 norm. It's valid to use the L1 norm in this context. You can generate different kinds of distance metrics. H itself doesn't have to be decreasing; it can be increasing. You could make H could be a sine function. You could imagine lots of ways in which you could build these things. So it doesn't matter that the point of radial is it depends only on the direction, only on the distance from a center, not the direction that you got to that center. Although I guess with the exception that you can skew your space a little bit. Okay. Good. So that's the idea of the radial basis functions, but in reality, people don't use radial basis functions as much as you'd think. Because there are lots of other choices for basis functions. I mean, you can use them, but well, maybe what I should do is I should recommend that you use radial basis functions only when you think that radial symmetry is important. So remember I said before that when you choose your basis set, when you're approximating your basis set, it's the best approximation within a particular class of functions. When you choose your basis set, it is telling you the class of functions that you care about. If I choose sines and cosines of low frequencies, I'm finding a low frequency approximation. If I choose sines and cosines within a range of frequencies, I'm finding a function that's approximation within that particular band. So if I'm choosing Taylor series up to the 10th order, I'm approximating for 10th order polynomials. So you can choose what you want the output to look like. In fact, you should choose what you want the output to look like. That choice is an important way of encoding your foreknowledge of the set of possible functions. And that knowledge could be because you want a particular output. I need a smooth output because I'm controlling a robot or the steering wheel of a car. Or it could be because you know that the real answer is smooth. For instance, that you know that all the noise is in high frequencies and the signal's in low frequencies, so I know the answer I want is in low frequencies. It could be any of those things. But it does represent constraints. So the choice of your Hilbert space, particularly if it's finite dimensional, is a constraint on the set of possible solutions. That's a good thing, right? Because what you can do is you can choose these constraints. You could ask for this thing to be band limited. You could actually smooth, low order polynomial. Almost all constraints are going to have something to do with smoothness, but it might be different smoothness in different directions, or it might even be things like different kinds of quantization in different directions, right? You could, these phi i's themselves don't necessarily have to be smooth functions, so long as you can define a norm and an inner product on them. So for instance, let me give you an example of a non-smooth one. Let's suppose that we're just taking that phi sub I is some Boolean function of x, right? We just have a bunch of different Boolean functions of x. So for instance, these could be Boolean polynomials, right? So this could be, if the x's themselves are binary, phi I could be, x1 and x2, or x3 and x4, or x5 and x6. I can imagine, creating a bunch of Boolean functions, and I could take combinations of those things, right? There are norms and inner products you can define on Boolean functions as well, although sometimes these don't satisfy a lot of they may or may not be Hilbert spaces depending on how you build it. But you can do this. The learning algorithms are going to be very different because you can't do differentiation anymore. LMS may not work the way you want, and linear combinations of Boolean functions are not Boolean. But the point is that you could do things like that, right? So you can choose constraints now. X1, X2, X3, and 4 could be the bits of X. And your constraints may be, or that you care, we only want to allocate so many bits to the first component of X, more bits to the second, fewer to the third. So now you may have constraints that tell you, that are about how I'm going to allocate resources in terms of information. So there's lots of different constraints that can be allocated that way. And what you want to think about, what you're asking the network to do. Let's see, I can get back to it. Come on back. Uh-oh. Oh, sorry, my pen turned itself off. There we go. What you're asking the network to do is this: find me the best solution within this class of functions. That's an important thing to realize, what these classes of functions are and how you're choosing them. So let's contrast that with multi-layer perceptrons. What's the multi-layer perceptron function? Well, it looks like this, right? And so we can use this same logic, the same way of thinking, to analyze multi-layer perceptrons, because in the end, I have some x, which creates some set of phi sub I of phi1 of x to phi n of x. And then I've got some output y, which is the linear combination of those. The only difference is that there was some stuff in between here, right? And then some magic happened that allowed that x to come up to these things. And that magic might in fact be a bunch of other layers, right? But let's just look at this top layer, which is what I mean going on here. So that top layer, and let's just look at that top layer for the case of a two-layer neural network. So now let's suppose that x here is a vector, these things go up to here just like we normally would. And then we're going to call this W. There's two W's, right? We've got W, maybe that's W1, maybe this is W2. But we've got the W's down here, which become these basis functions. Now, first of all, why does this thing behave like a Hilbert space? Well, it's not really. For one thing, let's suppose I have a finite set of W's, Wi. So I've got W1, W2, W3, each of these is vectors, right? So there's, I'm going to enumerate a bunch of vectors, and and these just go up to Wn, and those are the only ones that I can use, right? I'm not allowed to tune the weights of W. Somebody says, here's possible sets of weights, right? I'm going to give them, you got 1,000, pick the right set of weights, but those are the only ones you have to pick off this menu. If I do that, I now have a finite set of these. And that's a perfectly good Hilbert space, right? That's now a 1,000-dimensional Hilbert space. I could pick any one of those W's. Suppose I tell people, okay, I'm going to give you an infinite number of W's, but I'm still going to enumerate them, right? Here's W1, here's W2, here's W3. There's an infinite number of these, but I can count them for you, right? I'm going to give them to you in numbers. I still have a Hilbert space. This is fine because I have a finite number of these phi's. Suppose that I do it the way a neural network normally does, the way a multi-layer perceptron does, and I say W can be anything. It's just a vector of real numbers. Now it's uncountable. Now I have an uncountable basis set. Now I can't use that anymore, right? So now phi I can't index it with I. So these things are indexed by integers, right? It's uncountable, so I can't index it by integers anymore, right? So now that fails. So that is why general multi-layer perceptrons are not the same as basis function networks. Yes, they're basis functions, but there's an uncountable number of possible basis functions. You could always imagine that there's sort of all the basis functions, even if it was countable, there's all the ones you didn't use. And so your job is to pick the right ones. But in the network, in the multi-layer perceptron case, you are going to find a finite number of these, but the number of ones that you didn't use is actually uncountable. Once you've found these, once you've trained this lower level, now you're back to a finite number of these, and now it behaves like a Hilbert space again. But the point is, if you're using backprop, you're always allowed to change this lower level. So if that lower level is allowed to change any way it feels like, now you have an uncountable problem. But once these things are fixed, then you can treat the upper level the same. So that's the relationship between these. Now, one of the reasons that's important is because if you look at, suppose sigma here is a sigmoid nonlinearity, and so this is sigma of x, not some sigma nonlinearity, right? But I can do things to this, like I can make the make x very big, right? I can multiply. I could look at sigma of, say, ax, where a is a very big number. We'll look at this as a goes to infinity. If I do that, this thing, and sort of around 0, is going to get arbitrarily sharp. It'll always be differentiable as long as a is finite, but it's still going to get very, very sharp, right? So members of this class of functions, can be very sharp. So, and in fact, they can be as sharp as you want them to be. So it doesn't provide much of a constraint on how fast your function can change, right? If I take radial basis functions and they're all this particular shape, it can't be any sharper than this, right? That's the sharpest I can ever be, no matter how many of these things I add together, right? But if that's not strictly true, depending on if you allow these things to be arbitrarily close, you could put one up and one down, and you could add them together, but you have to allow these centers to move in toward each other. But for the most part, if I put these at fixed locations, then those that sharpness to this, this will limit you in some way. So the problem here, so the difference here is these radial basis functions, if you choose them to represent the class of functions that you care about, you can prevent overfitting with that. Remember, the overfitting problem is if I've got a bunch of points like that, do I fit it with this? Do I fit it with that? Or do I fit it with this? Right? All of these things are going through that set of points. And one way to do that is to do some of the stop training stuff we talked about before, or the book talked about in the previous chapter. One way to do that might be to regularize in some way, to say we just don't, or to limit weights in some way, or to do weight pruning, and there's a lot of different things we could do. But another way is simply to say that we're just not going to tolerate functions like this. They're not within the set of possible solutions. So we're going to choose basis functions that don't allow that. And so what happens is the choice of radial basis functions can prevent overfitting. And what you recognize is one of the ways you know that is because if these functions are fixed and are not allowed to change, in backprop they are, but in RBFs they're usually not, then all your training is this top layer that's trained with the LMS rule, which is guaranteed to converge. So you have so there's no concepts of local minima. There's no concepts of overfitting. It's going to converge to the best approximation within that class of functions. So this is kind of why you would choose one algorithm over another. It's this ability to specify these things. Let's see. There's a few more things I wanted to talk about. I'll just do more. Let's see. There was one other. Oh, I didn't talk about this. Let me back up a second. When you're looking at radial basis functions, again written like this, there's sort of how do you place these centers xi, and there's basically 3 different ways in which you could do it. One of which is you could just place them wherever you want, right? I'm just going to put centers this is a 2-dimensional space. Suppose this is x1, that's x2. I'm going to place them all throughout the space. I'm going to pave the space like this. Those are fixed locations. That's the easiest one to think of mathematically, right? We have a fixed set of basis functions. It fails badly as you go to high dimensional spaces, right? Even if I just have 2 basis functions per dimension, in this case I drew it as 4 or 4 basis functions per dimension, the number of required basis functions will go as 2 to the d, right? Where d is the number of dimensions. So it expands rapidly, and if x for lots of problems we deal with, for instance, maybe you're looking at image processing, d might be 4 million. So 2 to the 4 million is a very big number, and it's going to be hard to train all those basis functions. You're not going to have enough data to do it, even if you can calculate that or you have the storage for it. So the fixed basis functions have the easiest math, but in the end tend to be fairly impractical. Another one you can do is you place it just at the data points. So the reality is, even in these high dimensions, you only have so much data. So you watch your data come in. Here's x1, x2. I see this point, I see that point, I see that point, I see it. So I'm just going to put basis functions at the data points. Now, what happens if I care about a value out there? I don't know. It's undetermined. But the point is, I'm too far from an example to know. So this sort of says, look, if you see something that you've never seen before, don't make any guesses. The network isn't going to help you. But if you see something close to something you've seen before, I can make a prediction. So it remembers the data points, and it's basically sort of an interpolation, but not an extrapolation method. It says, okay, if I've seen 2 data points and I get something between them, I can make a guess as to what that would be. I can read out from those. And it's just like saying, if I did this in 1 dimension, I might have a bunch of data points here, and I might put some basis functions around those, and they may be spread out in different places. If I've never seen a data point here, I can't say anything about it. But I can say a lot about data points that I see within this region. So you tend to know more and make better predictions in regions where you have more data. That's good. That makes sense. The other thing that happens is it never forgets the training set. Like, the training set is always in there. It's a little bit like humans. If you have seen it before, then you should do it, right? If you haven't seen it before, you can make some guesses. But if you have seen it before, by no means guess. You remember, right? So it remembers. This has this sort of infinite memory property. And I would argue that a lot of things humans do have this sort of infinite memory property. We don't forget, you can't unsee something, right? You may misremember, but you can't unsee things. Once they're in, they're in. And if you see the same thing again, you can have the same reaction to it, or you can make the same prediction from it, right? So, but if you see something that's not exact, but is close, now you may say, oh, it looks a little like these 2 things. Let me kind of think about how those 2 things happened in the past and what I'd expect would be an average of those, right? So it has that property. In this case, the amount of storage grows as the number of data points you have, but it may be independent of the dimensions, right? So that can be a lot less. In general, for it depends on dimensionality, but you're not going to be able to extrapolate very much. But the data size is always limited by the amount. The network size is limited by the amount of data. Even if you have a lot of data, it's never gonna grow with recursive dimensionality. The third way you can do things is you can be adaptive, which is you move the centers around. And so you might notice that, okay, we start there, but I'm starting to get a lot of data in this region, so I'm going to just put a center on top of that. Right? And oh, wait a minute, now I'm getting a lot of data over here. I'm going to put a center on top of that. But the data here may be spread out, so I'm going to make this basis function bigger. Data here is all very narrow, so I'm going to put a small basis function there. So you could decide to move these basis functions in a way that will that will do its best job at approximating whatever function you want. There's a number of different ways to do that. If you have x is coming in this case, I'm sort of drawing as a two-dimensional x. I've got a bunch of basis functions up here. And I've got some output there. I could choose the locations of these basis functions, phi, based on the actual target function, f star of x, that I'm trying to accomplish, right? And one way to do that would be, you could use backprop, right? I mean, I could just adjust the weights. You could calculate, phi is a function of, is a smooth function of x minus, I'm going to write it as wi to emphasize that these things behave like weights. I could figure out what the derivatives are for this thing, and I could backprop through and actually adjust those weights using backprop. And that would be adjusting these functions for the particular desired output. There's another way you could do it, which is statistically, which is what I was suggesting here, which is you just adjust these weights just based on the statistics of x, right? Put lots more basis functions where there's high density of the input. You don't know what the output's going to be, but we're just going to adjust them. That's what might be considered an unsupervised algorithm. We haven't talked about that yet, but the idea where these hidden units are adjusted just based on the statistics of the input without knowing what the final function is that you're going to use. That's unsupervised. And there's a couple of different algorithms that are used for that. There's the k-means algorithm, and this thing's called expectation maximization. This chapter talks about k-means. The EM algorithms will be talked about later. EM algorithms have a very strong basis in statistical theory and are basically trying to approximate the probability distribution of the input, and these things. It's related to methods called kernel density estimation and others, where you're basically trying to you try to get the best representation of the probability distribution over the inputs x. That's EM and kernel density estimation basically do that. K-means is a heuristic algorithm, which sort of says, well, put centers near where the data tends to occur. And the way the k-means algorithm works is, if all the data points live at the same spot, I can see one point, I'm going to put my mean on that. I see another point, and I'm going to move my mean a little bit toward the second point. I get a third point, I move it there. I get a fourth point, I move it there. And so my mean value is going to wiggle around inside all the points. But if I do this long enough and I approximate it well enough, my average value is going to look like the average of those points. What you now do is you say, okay, suppose I have a different cluster of points coming in here. Well, first thing I do is I decide anytime a point comes in, I say, does it belong to this cluster or to that cluster? Right. So a new point comes in, some candidate point comes in here. And I say, which cluster is it closer to? And say, well, it seems to be closer to that. So I'm going to just use it to adjust the mean of this one, and I leave the other cluster alone. Now a different point comes in over here. Oh, it's closer to this guy. So now I'm going to use that just to adjust this one. So you only adjust the nearest cluster, adjust the mean of the nearest cluster. And if you do that, what will happen is over time, these things will converge so that you sort of have the means of clusters of points. It's a clustering algorithm. K-means is not guaranteed to find you the right answer in any sense. It's not even guaranteed to converge, but it very often does find good answers. Whereas the EM algorithms, we understand what the answers are, and it's actually optimizing a fit to a particular cost function. But it's important to recognize that just because I'm talking about basis functions, there are different ways of doing this. But the adaptive choice of basis functions is the closest thing to the way multi-layer perceptrons work. Again, remembering that adaptive choice of basis functions may make the whole thing not behave like a Hilbert space anymore. The reason it's important is once it stops behaving like a Hilbert space, it becomes very difficult to prove that you found the optimal answer. Most convergence algorithms are only provable within Hilbert spaces. Again, that's a level of complexity that you guys may not need to think about, but it's worth remembering the differences between what these algorithms do. The last thing I wanted to talk about here, just in terms of the math, is the Riesz representation theorem, which applies to something called these linear functionals. This takes me back to something I believe I did in the first or second lecture, which is looking at the expectation operator. If you remember, a functional is something that maps a function into a number, into a scalar. So an example of a functional might be the variance, right? The variance of a function takes a function f, calculates this integral, and creates a number from it, right? The variance, of course, is not linear. So if we talk about linear functionals, we might look at something like the expectation operator, which is a linear function. So it turns out that pretty much all linear functionals look like expectation operators. They'll be very similar. Essentially, all linear functionals in this class of spaces, the L2 normed Hilbert spaces, will have something like this. They will all look like the integral of f of x times p of x dx for some p, and this you'll recognize as the expectation over the probability density p of the function f. And that gives the expectation there, right? And in fact, you can generalize this a little bit by looking at the conditional expectation of f from z, which is based on the probability of x given z. Remember, z is can be almost thought of as a parameter, it's a value. And so in this case, the conditional expectation of a function given some observation z looks like a scalar of z, but it's a scalar that depends on z. This is important because z might be an observation. Z might be something that I see in the outside world, and I would like to predict what's the outcome, how is the output of this network or the output of some function going to change based on something else that I've just seen. That's where the conditional expectation is. What do I expect to see without any information? And oh, I got some information. How does that change my expectation? And that's what this shows. And these are linear functionals. The Riesz representation theorem, which has, when in its full formulations, is more complicated than this, but in the simplest form is that all linear functionals in a Hilbert space are equivalent to linear operations on the coefficients. So remember I said before, there's this sort of one-to-one mapping between functions and the coefficients of your basis set, right? So in some sense, this is just an extension of that. A linear functional that maps a function into a number can operate either on the original function or just on their coefficients. And that's fairly easy to see. Suppose I take the expectation operator of some function f, which I can represent as this superposition, as this combination over the basis set, right? So I can just exchange the order of, write out the expectation, exchange the order of integration and summation. And what you find is that looks like the sum, again, same coefficients of this term here, which is a scalar, right? This integral will just give me a scalar. I'm going to call that scalar m sub I. And then this product here looks like the product of two vectors, m transpose f. So now I have a vector operation. And again, this f is not meant to be, this is the function, this is the vector of coefficients. But there's this operation here on the coefficients, which did the same thing as this linear functional on the original function. And if you look at what these mi's are, this here is the expectation of sigma I. So if I know the expected output of my basis functions, I can calculate the expected output of any combination of those bases just as a sort of using a vector operation. And this becomes very important for the conditional expectation. The conditional expectation here of f given some observation z, if I know the expected output of my basis functions for each value of z, then I can calculate the expected output of any function just using this linear operation. And again, so if you imagine what that means is if I know, if I take a measurement and I want to predict the outcome of some computation, right? I have I've measured the wind speed, and I want to know, where the ball is going to land. But the way I'm calculating where the ball is going to land is based on some set of basis functions. Well, all I need to know is the wind speed effect on those basis functions, and then I can predict from that using using a vector operation where the ball is going to land. Now that doesn't sound like, why does that matter? I could have just done the same thing for knowing the ball is going to land, right? But I could do this for every type of ball, or for anything I might throw, or for anything else that's calculated from that same set of basis functions. So once I know the effect of a measurement on the basis functions, I know the effect of that measurement on anything I calculate from those basis functions. So these things become important when we start thinking about, and then again, I'm just trying to say, why does the math matter? The math here matters because it allows you to understand how these networks operate under a lot of different conditions, and it allows you to prove they converge, and it allows you to, in some ways, design different kinds of networks around this, particularly these kind of things. The last thing I wanted to say, and I just put that in here, he talks a lot in that chapter about the recursive least squares algorithm. You can try and figure it out the way he does it. I just want to point out it's the same as the Kalman filter. These are the Kalman filter equations. This is the recursive least squares algorithm, and for the most part, there's a one-to-one relationship between these things. You're just not used to thinking of Kalman filters operating on the weights. You usually like to think them on observations, but it's basically a Kalman filter on the weights. The equations are almost identical, and that's why it works. Kalman filters are good things. So I'm going to stop there and take questions. And as Jessica pointed out, you guys may, depending on, because I didn't look back at this, you may not have actually read this chapter yet, but this will then give you a taste of the thing you're going to read for Wednesday. But do people have questions about this? Not hearing a lot of questions. That's okay. So what I will do is, as usual, I will hang out for a bit. If people want to have things they want to discuss about this or the homeworks or other aspects, please stay on, and we can talk a little bit about that. And otherwise, we have class on Wednesday, and I will take a look at the schedule and make sure that I revise that and keep it up to date so people know where we're going and what to expect. Turn off the recording here.